I'm going to show you about that one. Yes, I'm going to show you how do we achieve that one. Okay, that could help your question. Okay, anyhow, once we know this relationship, then we can decide, say for example, once we can insert there is, we know DHKL, right? For the cubic system, DHKL has this relationship. We insert this one to the Braggs law. Actually, here we only consider n equal to 1. That means the first order diffraction. Because that one usually is a strong peak. Okay, give us a strong peak. And then when we insert that one, we can actually take out the square root. We get sine theta squared equals to this relationship. But don't forget, this one only works for cubic system. Okay, see for example, for monoclinic or other systems, the relationship of DHKL and A will be very different. Okay, this class we only consider the most simplest case. Okay, so from here then we can say, you know, when we do the X-ray analysis, the wavelength usually fixed is determined by the equipment, and A actually also kind of like a fixed number. It does not, you know, it's lattice structure, right? It's lattice constant, so it's a constant. So now if we, you know, see for example, if we define two different crystal planes, okay, one is called A plane, one is called B plane. Could it be 1, 1, 1, will be A, 1, 1, 0 will be B, okay? Then we can easily correlate using this equation, right? What we do, we just insert HKL from the HKL planes, right? Then we can get a relationship. Now, for the A plane, you use the HKL from that plane, and for the B plane, we get that, right? And then if we divide these numbers, what we can do, we can eliminate the lattice constants here. Okay, then what we get, because these numbers are usually known. See, for example, if we know HA equal to 1, right? For the A plane, 1, 1, 1 plane, then this one is a fixed number. Suppose the B plane is 1, 1, 0 plane, then that one also fixed number. Then their sine theta square ratio should be a fixed number. That is the way. I'm going to show you how do we use this equation to determine the crystal structure. That's, as I mentioned, this is the most simplest case, okay? Indeed, in reality, there's a lot of ways, there's a lot of, database available. You can compare your X-ray spectrum with the standard, spectrum, okay? Then you can guess what the metals or the crystal you are exploring. As I mentioned, to detect for the X-ray analysis, what we do, the equipment is quite straightforward. Okay, usually we want the samples to be polycrystalline, to be pounder shaped. So that means when you put, say for example, 1 gram of your sample, your metal samples, in the specimen chamber, the crystal could have, each of the particle could have different crystal plane facing the X-ray, right? So don't forget, in the 1 gram of a sample, you have a lot of particles, millions of those kind of particles. Each particle has a unique plane facing the incident light, right? So therefore, when you try to detect what happens here, what you do, you use kind of like a moment device. Your detector will move along different angles and then read out. Okay, say for example, when the angle is very small, there's no readout. But at a certain angle, when some of the crystal planes, don't forget, you have all those kind of possible crystal planes inside your sample. At a certain angle, when the Braggs law or the Bragg diffraction condition match, you will see a strong peak here. Okay, then when they move again, you will see at other angles, you will see a peak. So using that one, then what you will get, this is the standard, kind of like an exemplary X-ray spectrum, a spectrum here. So you will say this is actually a constant, okay, pounder constant. So you will see all possible planes coming out of the constant peak, and then you will say at a different crystal plane, you have a different intensity. So that's actually what you measured here. See, for example, when Actually, here we should use 2 theta. I forgot to mention that in the diffraction, X-ray diffraction spectrum, x-axis is usually a 2 theta angle. The diffraction angle is a 2 theta angle. So that means if you need to read out here from the spectrum, the first peak 110 corresponding to about 40 degrees, the diffraction angle should be about 20. You need to divide it by 2. Okay, so this is the 2 theta angle. So from there, actually, we can say at about when in the experiments here, when the detector at about the 20 degree, you will see the detector will see a large number. But at all the others, there's almost nothing there, except for some kind of a noise. Okay, the noise signal. So that means it's a very low cost at the beginning or the intensity. And then at a certain angle, you will see a sharp increase. Okay, that means at this angle, some of the crystal plane get detected. Or that means the X-ray at this angle, they match the Bragg law. They match the Bragg's diffraction condition. Yes?
So what you're really getting out of this is the distances, the number of wavelengths this is traveled, right?
You get the angle from the angle, right? Because from the spectrum, what you will get? You will get the angles, right? The diffraction angle, 2 theta angle. From the angle, what you can go? You can go either here, okay, because there's some rules, there's some specific rules for different crystal lattice structure. Okay, I'm going to explain that one later on. So from there, this number sometimes should be a fixed number. You should know about that. Okay, which peak corresponding to the first one, which peak corresponding to the second. Once you know that, or you can go up here. HKR is the fixed number, lambda is a fixed number. When you decide theta, you get A. That's an analysis. Okay, so that means you can explore what is the lattice constant of your crystal. Okay, because different crystals have different fixed lattice constant. Or another way, another information you can get from here is, indeed, for moly, see for example, or for tungsten, you will get, from tungstens, for the tungstens getting from, a factory in Florida and another one maybe from Pennsylvania. When you do the X-ray analysis, the Ponder X-ray analysis, if they're like 99.9% pure, their spectra should match each other. Does not matter where do you get that. Okay, at least, or maybe the peak intensity are different, slightly different, but their position and then the number of these kind of specific peaks should match each other. So indeed, if I see a spectra like that one, what my students do, they need to compare this spectrum with thousands or millions of existing X-ray spectrum already in the database. Okay, the computer can do the match. And the computer will match all these different 2 theta angles until they found one sample or one existing metals that have the same crystal structure or the crystal spectrum matches with yours. And then we can very confident to say, okay, this is that one. Okay, this is the typical one. Okay, but what you will get, the raw data you get from the X-ray diffractometer is like this. Okay, so yes.
How come not all the possible planes are showing up?
Very good.
No 111.
Okay, these are the special rows. Okay, for different, I'm going to cover that one here. Okay, for the BCC structure, not all the planes are allowed. You guys know about the, kind of like selection rows for the FTIR, for other, something similar to here, okay? Not all the planes will show up, okay? See, for example, for BCC structure, only when the HKL numbers are the even number, 111, do you get an even number? HKL, 111. No, because when you add up them, you get 3. 3 is not an even number. You will not see 111 plane in the BCC structure, okay, body center cable, okay? When only HKL are even, you will see this strong reflection peak. That means you will see a corresponding peak in the spectrum. Okay, let me ask you a question. Based on that, what will you guess about the tungsten? BCC, right? Because when you add up all these numbers, even number, even number, even number, all of them are even number. So most probably tungsten is a BCC crystal, yes.
Why is it that only even numbers show up on the fraction? Because only those exist for BCC, or is it because
No. All the other plans also show, BCC structure, you could have whatever plan, actually. Not that. That's, for this selection row, why? That's a good question. I didn't explore that one yet. I need to do some homework, but that's the selection row. Okay. Possibly. Okay. Let me guess on that one. I'm not very sure. I'm not saying you could not get all the number, from the BCC plan, like say for example 210 plan. No, you should be able to get that one. If we do the comparison with the typical selection row, see for example Raman spectroscopy or the FTIR, I believe it's related to some of the quantum states. So I'm not very sure. I haven't go deep into those kind of topics because not really covered in this class. It's way too complex. So, but for the BCC structure, we need to know for the even numbers, you will see the peak. For the FCC structure, what you will see HKL number, either they're all even or they're all odd. Not the mixture of them, not the combination. Some are even, some odd. For those, you will see a strong peak. Okay, see for example, 111 plan are all even numbers, so you will see a peak there. What do you think about 210 for the FCC structure? 210. No, you will not see because 2 and 0 are even numbers. 1 is not, right? It's kind of like that. Not all even or odd, so you will not see those kind of plans. Okay, so why not we stop here for a 5 minutes break, and then I want to finish that.